Hello and welcome to our next video presentation in hypothesis testing. This presentation is going to discuss z-scores, what they are, when do we use them, how do we use them, and also go through an example of using a z-score and interpreting what it's telling us. So let's start out with just defining what the heck is a z-score. Hopefully you have your notes pulled up. Again, these notes are available on Google Classroom. You will need to make a copy of the notes. You can't directly edit the notes document, but assuming you have the notes in your computer and they're open and you made a copy, we're ready to dive right in and start with just defining what is a z-score. Z-scores, these are also called standard normal scores. And these are numbers that tell us the distance between the mean and a score of interest. Now that's not a very exciting definition, but I'm not quite done. The z-score tells you the distance in units of standard deviation. You're like, oh yay, that makes a lot of sense. I understand if it doesn't totally make a lot of sense. And that's partially why we have to go through an example and I have to show you what I'm talking about. But where we left off last time, we had talked about the standard normal curve. And this is what I'm talking about when I mean the z-score will give you the distance in terms of units of standard deviation. Because when we've standardized our data and we assume that it's falling in this normal distribution, we set the mean to 0 and then standard deviation units are in increments of 1, both going out to the right and moving to the left. So in our z-score, we will use those numbers to indicate where in the curve or what area underneath the curve we're looking at when we're comparing a score of interest to the mean. And so I guess the next thing that's probably you're scratching your head about is like, when would you actually ever use this? And I'm going to be real honest here, not a whole lot. Most of the time when you're getting into statistical analysis, you're going to be doing some of the tests that come further along in the semester. But z-score is a really, really important foundational tool, and you need to understand what they are because the analyses that follow build upon these same concepts. So it is really important that you know what these are and kind of understand how to use them. So you use the z-score to determine the proportion of cases or scores that are included between the mean and any z-score in a normal distribution. Oh man, let's fix all my spelling. Spelling is hard. So you can also use a z-score to figure out the proportion, and you can also use it to figure out a score. So let's say you know a proportion or percent that you're interested in. You can figure out the z-score and then the score or value of interest you would need or that corresponds with that percentage. Again, if this doesn't make a whole lot of sense, just hold tight with me. Let's actually work through an example. So first, let's start with the formula, the z-score formula. Here it is in all its glory. And one of the things that I never liked, particularly about regular math classes, is that they would give you these formulas and they would just breeze right through it. And I was one of those people that just struggle with this kind of language. So I like to take the time to explain what every letter in this formula means and what it's talking about. because this is something that I don't want to be intimidating to you. I want you to feel like, you know, you can work this formula. And some of you are going to look at this and be like, I've seen this before. I've done this in other classes. I'm cool with it. And if that's you, just like skip ahead a few minutes and catch back up when we start with the example. But if this is new to you, I don't want to assume that you're comfortable with it. So again, I'm going to define what each of these letters are. So the z-score is, this is the distance between the mean and the score of interest in terms of standard deviation. Oh, not m. Don't do that. Leave it as mu. Okay, so this funny looking u is the Greek symbol for mu. And this is the symbol for the mean, particularly the population mean. When we have a sample, we'll use x bar, so this letter x, and it will have a little bar over the top, and that indicates that we're talking about an average, but an average specific to a sample. When you see the Greek letter mu, it's either talking about mean as a, like, the mean, or it's talking about mean in terms of, like, we actually think we know what the population average is, and this is the number that we think it is. And to indicate that we're talking about population, we would use mu, or if we're talking about things in a theoretical sense. But as we move into more statistical analyses, you won't see mu as often. You're more likely to see x or x bar. In this case, for the z-score formula, the x is your score of interest. And then lowercase s is the standard deviation. You might also see standard deviation as sigma. As sigma. Let me insert the symbol, which this is good to know. You want to know how to insert symbols because you'll need to use this for your formulas when you do your homework. So to insert one of these special little things or these special formulas, you would go up to insert and then either special character if it's just a symbol you're using, or if you're actually going to put in a whole equation, then you would go to equation. For right now, I just want to show you the symbol for sigma, and there's multiple ways you can do it. You can scroll through all of this business and it goes on and on and on. You can type in by word what you're looking for. You can also kind of draw it with your mouse and it will pull it up. So I'm going to show you sigma looks like this. Let's see what it does. There it is. Hello, sigma. Wait, no, you're not sigma. This is sigma. Greek letter sigma. So let's see if it put it in there. Yep, when you click on it, it inserts it in there. So then I'm going to close this and I'm done there. So that's kind of a cool little feature. It's something handy to know. So sigma is another common Greek symbol that we use a lot in statistics, mu and sigma. And so these are things that when you see them, I want you to start familiarizing yourself with what are they telling you. So when you see sigma, it means you're talking about standard deviation. When you see mu, it means you're talking about the mean. All right, so how do we actually use this formula? Let's scroll down here. I always like to start with an example. I think that stories help with statistics because they help ground some of this sort of abstractness in something that feels more approachable, more like reality. So I don't know if you had this experience when you were in elementary school or junior high, but there used to be a rule, at least in the state of Missouri where I grew up, that if you didn't score high enough on the standardized test, the MAP test or the achievement test, they would hold you back. And then at some point, they made the decision that all those students who were held back were just going to skip forward and rejoin their cohorts, which was very exciting for me because there was this boy that I liked who played the saxophone, and he hadn't been in our grade, and then walked into 8th grade and there he was in band, and it was very exciting. He was never really interested in me, but that's okay, it was his loss. Anywho, my story comes from, you know, I don't want you to think I completely make this stuff, even though a lot of this is just made up. But there used to be these policies that they would just basically pick a score, and if you didn't reach that score, then there were some really dire consequences, like being held back a grade. So in this story, let's pretend that you work in the State Department of Education And there's a state superintendent who wants to know if they were to implement this policy where students who don't reach this cutoff score are held back, like what would be the implications? So they determine that the cutoff is going to be 120 on whatever scale. And if you do not score a 120 on the exam, on the state standardized testing, you're in danger of being held back a grade. So you look at the data and you go back years and years and years, and you see that over time, historically speaking, the average was 135 and there was a standard deviation of 22. We're going to assume that it's a normal distribution and that this is a representative historical database. So what we want to know is like, okay, if we set the cutoff at 120, how many students is this going to be? Like what percent of our student body is going to be held back a year? This is where z-scores can be useful. So let's come in here under A and start figuring this out. So one thing to note, you might be looking at this and being like, well, look, historically, we score on average a 135 and 120 is like lower than that, so this is going to be fine. Like, it's probably not a big deal. This is where the statistics are actually really helpful because they can tell you, give you an indication of like, is this a big deal? Would this be a lot of people? Is this a big percentage? Or is this okay? Is it a really small percentage? So first, let's just set up our formula. We're going to have z is equal to, and we know, let's go back up here. We know mu. Mu is our historical average, our population average. We're going to say that is the 135. And we're going to subtract from that our score of interest. And our score of interest here is 120. And after we do that, we're going to divide that by the standard deviation of our historical information from the database, which is 22. So this is where you need to pull out your calculator, and we can race and see who gets there first. But let's see, what's 135 minus 120? Ooh, that's 15. I'm going to just go down here to the next line. So this is going to be 15 divided by 22, and let's see, what is that? That equals 0.68. Okay, so then you're like, awesome, z equals 0.68. Well, what the heck does that mean? Well, we're not done yet. So this is where you would go to the z-score table. Now the z-score table I have made available to you in our Google Classroom. So if you go back to Classroom, look under Classwork, and then go down to Hypothesis Testing, there is a link for the z-score table. And this is called Appendix B, the Standard Normal Table. I am going to move this over here so that you can see it. And the Standard Normal Table is what helps you then do this next step. So we have our z-score. Our z-score is, oh man, I already forgot. Oh, 0.68. So then what we're going to do is we're going to read under this column for z. And we're looking for 0.68. We're going to have to go down to the next page. 0.68. Oh, here it is. Okay, let's zoom in. See if I can do this. Here we go. Zooming in, 0.68 right here. Okay, so these are the two numbers that we need to pay attention to. This first number, this 0.2517, gives you the area between the mean and our cutoff score. So let's make a note of that number. 0.25, what is it? 2517. This is the area between the mean and our score of interest, 120. The other number is 0.2483. 0.2483. This, oh, that's an ugly arrow. Let's make a pretty arrow. This is the area beyond 120. So if we look up here at our standard normal curve, it's a positive number, meaning that it's to the right. But the thing that you should know is that the z-score table is always positive numbers. They're They don't give you the positives and the negatives, and that's because it's a mirror image. It would be the same numbers if negative if it was to the left. I'm not so interested that you know on which side of the curve this is happening, but I will just tell you, since our average is 135, it would be here, and then we're comparing it to a score of 120, which is to the left because it's smaller. The first number that we got, that 0.25, is B. It is giving us the area between the mean and our score of 120. The second number is C. That's the area beyond our cutoff score of 120. And that's actually the number we're more interested in. So if we come down here, I'm going to highlight this because this is the one that we care about. And what this is telling us is that that number, that 0.2483, that is the proportion of students who would be held back if we set the cutoff score to 120. Another way to think about that is if you multiply that proportion by 100, it turns it into a percent. So we would say there is 24.8% of students would be below the cutoff of 120. In essence, almost 25% of the students who take this test would fail. They would be below that cutoff and potentially held back. So even though 120 seems, like a small number compared to 135, that's actually a lot of people. 25% is a lot. If we know the population of students in the state who could be affected by this, we can actually find out roughly an estimate of how many students this would impact. And the way that you do this is you're going to multiply this proportion, the 0.2483. 0.2483, you're going to multiply that by the population, 1,030,121. And let's see, I'm going to pull up my calculator and let's do this. 0.2483 times 1,030,121, 255,779. That is the number of students that would fail and be held back. So then the last question, I'm just going to take this down to the next page. This is where I ask you, okay, you've figured out the numbers. Now we need to put the numbers into context. Like what would happen if the state decides to do this and the superintendent moves forward? So I asked this question, would this percentage and number be politically acceptable? And I want you to think about this. How do you think parents would respond if they find out their dear child has now failed based off of the score of a test and is going to be held back? And not just a couple of parents, but almost, like over 250,000 parents are going to find out this information. What do you think that they would do? They would probably storm the next school board meeting and be like screaming bloody murder about how unfair this is and how there's no way in heck they're going to hold their kid back. This is a large population. So one of the things that I always ask you to do when we do a statistical analysis is at the end is talk a little bit about, okay, so what does this actually mean? What are the implications of this? It's easy once you get comfortable with the numbers to just work the formula, do the formula, and then sometimes we forget to think about what are the implications of these numbers. How is this going to impact people in real life? This is all that we are going to cover for Z-score testing. If you have questions or would like to do some additional follow-up work, I'd be happy to meet with you. So please send me an email, send me a Snapchat, and we will be in touch. After this video, you need to move on to do the video and notes that cover independent samples t-tests and then the difference of means test.